The tap rule, detailed in NEC section 240.21, governs the number of overcurrent devices that can connect to a single busbar. This rule dictates that the total load current of all overcurrent devices connected to a busbar should not exceed 80% of the busbar's ampacity. In a situation involving a 100 amp main lug-only panel, or MLO, with lugs wired to the bus instead of breakers, and each lug feeding a downstream breaker via an SIS control wire over a 12-inch distance, and with 18 such breakers, the cumulative load current from these 18 breakers could easily surpass the 80% threshold of the busbar's ampacity, thus violating the tap rule. Installing a main breaker in the panel can address this issue and promote tap rule compliance by acting as a limiting factor on the total load current drawn by all overcurrent devices connected to the busbar. Furthermore, the main breaker serves as a protective measure for the panel and its internal components in the event of a fault condition. Implementing a 100 amp main breaker to the panel is an effective strategy to ensure adherence to the tap rule. Firstly, review NEC section 240.21 to fully understand the tap rule requirements and limitations based on the specific installation. Secondly, calculate the total load current of all the downstream breakers connected to the lugs in the MLO panel. Ensure that this total load does not exceed 80% of the panel's busbar ampacity, which in this case is 100 amps. Thirdly, select a main breaker with an appropriate ampacity rating that is suitable for the panel and the connected load. A 100 amp main breaker as suggested is a viable option, but it is crucial to verify that it aligns with the overall system requirements. Fourthly, install the main breaker in the MLO panel according to the manufacturer's instructions and all applicable electrical codes and standards. Fifthly, properly connect the main breaker to the panel's busbars, ensuring secure and reliable connections. Sixthly, verify the wiring and connections to all downstream breakers and control wires, guaranteeing they are correctly installed and meet code requirements. Seventhly, test the entire system after installation to confirm that the main breaker functions correctly and provides overcurrent protection to the panel and downstream circuits. Eighthly, label the main breaker and all other relevant components clearly to facilitate easy identification and future maintenance. Ninthly, document all the modifications made to the electrical panel, including the installation of the main breaker and any related wiring changes. Tenthly, consult with a qualified electrical inspector to ensure that the installation complies with all applicable codes and regulations and to obtain the necessary approvals. In more detail, the National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations, and understanding the specific sections related to overcurrent protection and conductor sizing is vital for ensuring a safe and compliant electrical system. Firstly, NEC section 240 covers overcurrent protection, including the requirements for overcurrent devices, such as circuit breakers and fuses, and their proper application in electrical circuits. Secondly, NEC section 240.21 specifically addresses tap conductors, which are conductors that are tapped from a larger feeder or branch circuit conductor. This section outlines the conditions under which tap conductors are permitted and the requirements for their overcurrent protection. Thirdly, NEC section 310 provides guidance on conductor ampacity, which is the maximum current a conductor can carry continuously under specific conditions without exceeding its temperature rating. This section includes tables and calculations for determining the appropriate conductor size based on the ampacity of the circuit and the type of insulation used. Fourthly, NEC section 408 covers switchboards, switchgear, and panel boards, including the requirements for their construction, installation, and overcurrent protection. This section is relevant for ensuring that the MLO panel and the main breaker are installed and protected in accordance with code requirements. Fifthly, NEC section 110 provides general requirements for electrical installations, including the need for proper workmanship, equipment labeling, and accessibility. This section emphasizes the importance of following manufacturers' instructions and ensuring that all electrical work is performed by qualified individuals. When evaluating the tap rule in relation to the 100 amp MLO panel, it is essential to consider the specific requirements outlined in NEC section 240.21. The tap rule allows for the installation of tap conductors without overcurrent protection at the tap point under certain conditions. However, these conditions include limitations on the length of the tap conductor, the ampacity of the tap conductor, and the overcurrent protection provided at the end of the tap conductor. Firstly, the length of the tap conductor must not exceed certain limits, typically 10 feet or 25 feet, depending on the specific application. Secondly, the ampacity of the tap conductor must be at least 1/3 of the ampacity of the feeder or branch circuit conductor from which it is tapped. Thirdly, the tap conductor must be protected from overcurrent at its termination point by an overcurrent device rated no more than the ampacity of the tap conductor. In the case of the 100 amp MLO panel with 18 individually mounted breakers connected via SIS control wires, it is crucial to assess whether the tap conductors, which are the SIS control wires, comply with the tap rule requirements. If the SIS control wires are considered tap conductors, their length, ampacity, and overcurrent protection must meet the conditions outlined in NEC section 240.21. If the tap conductors do not comply with the tap rule, installing a main breaker in the MLO panel can provide the necessary overcurrent protection and bring the installation into compliance with the code. The main breaker acts as the overcurrent device at the termination point of the tap conductors, ensuring that they are protected from overcurrent in accordance with the tap rule. The selection of an appropriate ampacity rating for the main breaker is crucial for ensuring both overcurrent protection and compliance with the tap rule. The main breaker must be rated to carry the expected load current of the downstream breakers while also providing protection against overloads and short circuits. Firstly, calculate the total load current of all the downstream breakers connected to the MLO panel. This calculation should take into account the continuous and non-continuous loads served by each breaker. Secondly, select a main breaker with an ampacity rating that is at least equal to the total calculated load current but not greater than the ampacity of the panel's busbars. In this case, since the panel has a 100 amp busbar rating, the main breaker should not exceed 100 amps. Thirdly, consider the potential for future load growth when selecting the ampacity rating of the main breaker. It may be prudent to choose a slightly higher ampacity rating to accommodate future expansion or increased load demands. Fourthly, verify that the selected main breaker is listed and labeled for use in the specific MLO panel and that it complies with all applicable UL standards. In addition to ensuring compliance with the tap rule, installing a main breaker in the MLO panel provides several other benefits, including enhanced safety, improved reliability, and simplified maintenance. Firstly, a main breaker provides overcurrent protection for the entire panel and all downstream circuits, minimizing the risk of electrical fires and equipment damage in the event of an overload or short circuit. Secondly, a main breaker allows for easy disconnection of power to the entire panel for maintenance or troubleshooting purposes, improving safety and efficiency. Thirdly, a main breaker simplifies the coordination of overcurrent protection devices, ensuring that the main breaker trips before any of the downstream breakers in the event of a fault, preventing unnecessary outages. Fourthly, a main breaker provides a single point of control for the entire panel, making it easier to manage and monitor the electrical system. When installing the main breaker, it is essential to follow the manufacturer's instructions and all applicable electrical codes and standards. Firstly, ensure that the main breaker is properly installed and connected to the panel's busbars. Secondly, verify that all wiring and connections are secure and that the proper torque is applied to all terminals. Thirdly, test the main breaker to ensure that it functions correctly and provides overcurrent protection. Fourthly, label the main breaker clearly to indicate its function and ampacity rating. Fifthly, document all the modifications made to the electrical panel, including the installation of the main breaker and any related wiring changes. Sixthly, consult with a qualified electrical inspector to ensure that the installation complies with all applicable codes and regulations and to obtain the necessary approvals. The one-line diagram is a simplified representation of an electrical system that shows the major components, such as transformers, switchgear, panel boards, and circuit breakers, and their interconnections. The one-line diagram is used to analyze the performance of the electrical system, to coordinate overcurrent protection devices, and to troubleshoot problems. When creating a one-line diagram for the 100 amp panel with the added main breaker, it is essential to include all the relevant information, such as the ampacity ratings of the busbars, breakers, and conductors, the voltage levels, and the location of all overcurrent protection devices. Firstly, show the 100 amp panel as a rectangle or square with a busbar ampacity rating indicated inside. Secondly, represent the main breaker as a circle or square connected to the busbars with its ampacity rating indicated nearby. Thirdly, show the 18 downstream breakers as circles or squares connected to the busbars via lines representing the conductors with their ampacity ratings indicated nearby. Fourthly, indicate the voltage level of the panel, such as 120 volts or 240 volts. Fifthly, label all the components clearly to facilitate easy identification and understanding. Sixthly, use standard symbols and conventions to ensure that the one-line diagram is easy to read and interpret. By including all the relevant information and using standard symbols, the one-line diagram can be a valuable tool for analyzing and maintaining the electrical system. In addition to the technical aspects of installing a main breaker and complying with the tap rule, it is also important to consider the safety implications of working with electrical systems. Electrical work can be dangerous, and it is essential to take precautions to minimize the risk of injury or death. Firstly, always energize the circuit before working on any electrical equipment. Secondly, use properly insulated tools and equipment. Thirdly, wear appropriate personal protective equipment, such as safety glasses and gloves. Fourthly, follow all applicable safety codes and regulations. Fifthly, never work on electrical equipment when you are tired or distracted. Sixthly, if you are not comfortable working with electrical systems, hire a qualified electrician to do the work for you. By following these safety precautions, you can minimize the risk of electrical accidents and ensure that your electrical system is safe and reliable. In summary, adding a main breaker to a 100 amp panel can help comply with the tap rule by limiting the total load current of all overcurrent devices connected to the busbar. The main breaker also provides protection for the panel and its contents in the event of a fault. When selecting a main breaker, it is important to consider the ampacity rating, the listing and labeling, and the potential for future load growth. Installing the main breaker according to the manufacturer's instructions and all applicable electrical codes and standards is crucial. Creating a one-line diagram of the electrical system can be a valuable tool for analyzing and maintaining the system. Finally, always take safety precautions when working with electrical systems to minimize the risk of injury or death. By following these guidelines, you can ensure that your electrical system is safe, reliable, and compliant with all applicable codes and regulations. Remember to consult the latest edition of the NEC and local electrical codes for specific requirements and regulations in area. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician for any electrical work or modifications to electrical systems. Additionally, proper documentation of all electrical work is essential for future reference and maintenance. Keep accurate records of all modifications, upgrades, and repairs performed on the electrical system. This documentation should include details such as the date of work, the components installed or replaced, the wiring diagrams, and any test results. This information can be invaluable for troubleshooting problems, planning future upgrades, and ensuring the safety and reliability of the electrical system. Furthermore, regular inspections and maintenance of the electrical system are crucial for preventing problems and ensuring its continued safe and reliable operation. Schedule periodic inspections by a qualified electrician to identify any potential issues, such as loose connections, damaged wiring, or overloaded circuits. Address any identified issues promptly to prevent them from escalating into more serious problems. Additionally, perform routine maintenance tasks such as cleaning electrical panels, tightening connections, and testing overcurrent protection devices to keep the electrical system in good working order. By implementing a comprehensive maintenance program, you can extend the lifespan of your electrical system, reduce the risk of electrical failures, and ensure the safety of your property and occupants. Lastly, stay informed about changes and updates to electrical codes and standards. The NEC and local electrical codes are constantly evolving to reflect new technologies, safety concerns, and best practices. It is important to stay up to date on these changes to ensure that your electrical system complies with the latest requirements. Subscribe to industry publications, attend training seminars, and consult with qualified electricians to stay informed about the latest developments in the electrical field. By staying informed and proactive, you can ensure that your electrical system remains safe, reliable, and compliant with all applicable codes and regulations. Moreover, consider the environmental impact of electrical installations and practices. Implement energy-efficient measures to reduce electricity consumption and minimize your carbon footprint. Use energy-efficient lighting appliances and equipment. Install occupancy sensors and timers to turn off lights and equipment when they are not in use. Optimize the operation of heating, ventilation, and air conditioning or HVAC systems to reduce energy waste. Promote energy conservation among building occupants. By adopting sustainable electrical practices, you can reduce your environmental impact and save money on energy bills. Also, be aware of potential electrical hazards in the workplace and at home. Identify and address any electrical safety risks, such as frayed cords, overloaded outlets, and exposed wiring. Educate employees and family members about electrical safety precautions. Install ground fault circuit interrupters, or GFCIs, in areas where water is present, such as bathrooms, kitchens, and outdoor locations. Use surge protectors to protect electronic equipment from voltage spikes. Develop and implement electrical safety procedures to prevent accidents and injuries. By prioritizing electrical safety, you can create a safer environment for everyone. In addition to the above points, it's important to consider the specific application and environment when designing and installing electrical systems. Firstly, for industrial applications, ensure that the electrical system is designed to withstand the harsh conditions and heavy loads typically encountered in industrial environments. Secondly, use robust and durable equipment that is suitable for the specific application. Thirdly, implement grounding and bonding systems to minimize the risk of electrical shock and equipment damage. Fourthly, for commercial applications, ensure that the electrical system is designed to meet the needs of the business and its customers. Fifthly, provide adequate lighting and power for all areas of the building. Sixthly, install emergency lighting and backup power systems to ensure safety and continuity of operations in the event of a power outage. Seventhly, for residential applications, ensure that the electrical system is designed to meet the needs of the household and its occupants. Eighthly, provide adequate outlets and lighting in all rooms. Ninthly, install smoke detectors and carbon monoxide detectors to protect against fire and carbon monoxide poisoning. Tenthly, follow all applicable building codes and regulations. By tailoring the electrical system to the specific application and environment, you can ensure its safety, reliability, and performance. Understanding the different types of electrical loads is crucial for designing and installing electrical systems that can handle the demands placed on them. Firstly, resistive loads, such as incandescent lights and heaters, draw a constant amount of current when voltage is applied. Secondly, inductive loads, such as motors and transformers, draw a varying amount of current depending on the voltage and frequency of the power supply. Thirdly, capacitive loads, such as capacitors and electronic circuits, store electrical energy and release it back into the circuit. Fourthly, nonlinear loads, such as electronic devices and power supplies, draw current in a non-sinusoidal waveform, which can create harmonic distortion in the electrical system. By understanding the characteristics of different types of electrical loads, you can select the appropriate wiring, overcurrent protection devices, and equipment to ensure that the electrical system can handle the load safely and efficiently. Also, it's important to understand the different types of wiring methods and materials that are available for electrical installations. Firstly, non-metallic sheath cable, or NM cable, is a common type of wiring used in residential applications. Secondly, metallic conduit, such as electrical metallic tubing, or IMT, and rigid metal conduit, or RMC, is used in commercial and industrial applications. Thirdly, flexible metal conduit, or FMC, is used to connect electrical equipment that may need to be moved or adjusted. Fourthly, armored cable, or AC cable, is used in applications where the wiring needs to be protected from physical damage. Fifthly, underground feeder, or UF cable, is used for underground electrical installations. Sixthly, direct burial, or DB cable, is designed for direct burial in the ground without the need for conduit. By understanding the characteristics of different wiring methods and materials, you can select the appropriate wiring for the specific application and environment.